Hey AP Physics students, my name is Nikhil and Mr. McMur had me set up a challenge for all of you. Today we're going to explore the mechanics that govern planetary motion. These are Kepler's laws, the very rules that guide the planets in their orbit around the sun. First, I'll explain each of the concepts, and after, we'll do some example derivations in order to really understand how these working parts interact. First, let's demystify the path planets take. The ellipse. An ellipse, as a conic section, can be simply explained as the shape you get when you slice through a cone at an angle that is not parallel to the base of the cone. Imagine you have a cone made of paper, and you cut through it with a pair of scissors. If you cut straight across, parallel to the base, you'll get a circle. But if you tilt your scissors so that you're cutting at an angle, the shape on the cut surface will be an ellipse. Some quick information to know. An aphelion is the greatest distance between a planet or other body and the Sun. The perihelion is the closest distance from the Sun. The ellipse looks like an oval and has two special points called foci. The singular would be focus. The sum of the distances from any point on the ellipse to make these two foci is always the same. This property is what defines an ellipse and is also what makes it different from a circle, which has only one central focus point. In the context of Kepler's laws, the orbits of planets around the Sun are ellipses with the Sun at one focus, not at the center. This means that a planet is sometimes closer to the Sun at the perihelion and sometimes further away at the aphelion, and this is why the speed of the planet changes as it orbits the Sun, which is described by Kepler's second law. Now, let's get started. Kepler's first law, the law of ellipses, tells us that planets orbit the Sun in an elliptical path, with the Sun at one focus, not the center. Let's take a look at a scenario. An asteroid named Helios orbits the Sun with a perihelion distance of 0.5 AU and an aphelion distance of 3 AU. Determine the semi-major axis, the eccentricity of Helios' orbit, and its speed at perihelion, assuming the mass of the Sun is 1.989 times 10 to the 30th kilograms. Okay, so I'm going to work you through the steps of derivation. At the end, you can sub in for the answers on your own. Use it to apply the concepts to the challenge problems that Mr. McMur gives you guys. So let's define our semi-major axis, which will be A. And our semi-minor axis, which will be B. Okay? An ellipse is defined by these two axes, which are perpendicular to each other at the ellipse's center. The semi-major axis is half the length of the longest diameter of the ellipse, and the semi-minor axis is half the length of the shortest diameter. This step sets the stage for understanding the dimensions of the elliptical orbit. Now, our next step will be to express A, the semi-major axis, in terms of little q and big Q. So, little q will be perihelion. Oh, forgive me, my stylus just died. Let me change that quickly. Right, so little q is perihelion, and big Q is aphelion. And the semi-major axis is the average of the perihelion and aphelion distances, because these are the minimum and maximum distances from the focal point, which would be the Sun, to the orbit's edge. And this step mathematically relates the semi-major axis to the actual distances in the orbit, and it can be expressed as A equals little q plus big Q over 2. Now, our next goal is to define the eccentricity, or E, of an ellipse as the ratio of the distance from the center to a focus over the semi-major axis. So eccentricity is a dimensionless number that describes the shape of the ellipse. An eccentricity of 0 corresponds to a perfect circle, while an eccentricity closer to 1 indicates a more elongated shape. This step introduces a new orbital parameter that characterizes the orbit's deviation from circularity. So let's express the distance from the center to a focus C in terms of, again, little q and big Q. The distance from the center of the ellipse to either of its foci, which will be represented by C, is directly related to the ellipse's eccentricity. This distance can be found by taking half the difference between the aphelion and perihelion distances, and this step links the geometric properties of the ellipse to the orbital parameters, and can be expressed by big Q minus little q all over 2. Okay, and now in order to derive the eccentricity E using C and A, we derive the ratio of the distance from the center to a focus over the semi-major axis. So this final step combines the geometric understandings of the ellipse, the physical parameters of the orbit, to yield the eccentricity. So we get E equals C over A, which will in other words be, if I had to write it out, Q, big Q minus little q over 2 over little q plus big Q over 2. And what this will actually give us is the equation big Q minus little q over big Q plus little q. Okay, and that will be our eccentricity formula. In order to apply it to the original problem, you can sub in a value of 0.5 AU for little q and 3 AU for big Q into the derived formulas in order to find the semi-major axis and eccentricity. Now, Kepler's second law, the law of equal areas, states that a line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. This implies that the planet's velocity is not constant. It's fastest at perihelion and slowest at aphelion. So let's take a look at another scenario. A comet named Cometra passes its perihelion at a distance of 1 AU from the sun and moves to its aphelion at 8 AU. If it sweeps out an area 3 times 10 to the 13th meters squared in 24 hours at perihelion, find the speed of Cometra at perihelion and aphelion. Okay, so let's take a look. And quickly, before we begin this problem, I just want to restate Kepler's second law. Equal areas are swept in equal times. This law states that a line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. And what this implies is that the planet moves faster when it is closer to the sun and slower when it is further away. And this conservation of angular momentum is a fundamental concept in orbital mechanics. So let's express the area swept, which will be A. A is area swept. Please forgive my writing. Area swept as a function of the speed v and time t. The area swept out by the line segment can be approximated by the area of a triangle with base r, the distance from the sun to the planet, and height v dot t, which is a representative of the distance the planet travels in time t. Actually, this is a concept you guys should very well know by now. Change in x equals v times t, right? So basically what we're just doing, we're connecting a little triangle here and say if this was the total sort of orbit, this is the area swept right here, and this is radius r, right? And then this can be represented right here by v times t, okay? And so this step mathematically relates the physical quantities of speed, time, and distance to the area swept out, as dictated by Kepler's second law. And so in other words, this can be, the formula for a triangle, of course, is area equals 1/2 base times height, right? So in order to express this properly, we would actually get area equals 1/2 RVT, okay? And Now we want to rearrange the equation to find the orbital speed v. And so essentially, all of you guys have taken algebra now, you know how to isolate quantities, but I'll just work it out for you quickly. You want to multiply the 2 over, so you get 2a equals rvt, and then in order to isolate v, we divide by r and t, or to get v. And this right here will be your formula for orbital velocity, right? But I just want to introduce a brief concept, like I mentioned earlier. In orbital mechanics, we have something which you'll also apply to a smaller scale, but the concept of angular momentum, or L, conservation. And I'll just write that out. L is angular momentum, right? So our formula for that would be L equals mRV, right? Where m is the mass of the comet Cometra, and angular momentum is a conserved quantity in a closed system where no external torques are acting, and you guys will learn about that a little later, so don't worry about it. For a comet orbiting the sun, the product of its mass, m, the distance from the sun, r, and tangential speed, v, remains constant. And this step ties the concept of conservation of angular momentum to the observable quantities in the comet's orbit, right? So briefly, since we have this formula right here, which gives us v, we actually want to find the relationship as well of v in reference to L, and when m and r are held constant. And since the mass of the comet does not change, and the distance r is known at perihelion and aphelion, we can deduce that the speed v must adjust to keep the angular momentum L constant. And this step solidifies the relationship between speed and angular momentum, reinforcing the implications of Kepler's second law. And so what we can actually express this as is v is proportional to L over mr. And here is our second relationship to note. And just to wrap up this problem, if you did want to solve it, you could substitute the area is 3 times 10 to the 13th meters squared. The t would be 24 hours. R sub p is 1 AU for perihelion. R sub a is 8 AU for aphelion. And that will help you find the orbital velocity. Now, Kepler's third law, the law of harmonies, relates the orbital period of a planet to its average distance from the sun. Specifically, the square of the period t is proportional to the cube of the semi-major axis A. So, let's take a look at one last example problem. If a hypothetical planet orbits the sun with a semi-major axis of 4 AU, how long is its orbital period? Now, how would we start? Let's think again. Let's state Kepler's third law. The square of the orbital period is proportional to the cube of the semi-major axis. I'll give you guys a second to think. This law provides a precise mathematical relationship between the time a planet takes to complete one orbit, otherwise known as its orbital period, and the size of its orbit, specifically the semi-major axis. It reflects the balance of gravitational forces and inertia in planetary motion. So first, let's write the proportional relationship for a planet X. Okay, so we can express Kepler's third law, setting the stage of a comparison with any other planet's orbit around the same star. So let's do p sub x squared is proportional to a sub x cubed, right? And this represents, let's say, planet X. Now let's do the same thing for, say, a planet Y. So we have the same type of proportional relationship, and this step allows us to compare the orbits of two different planets and find a connection between their orbital periods and semi-major axes. So now we have the same thing essentially, p sub y squared is proportional to a sub y cubed. Now, let's set up the proportionality as an equation using the constant of proportionality k. By introducing k, we can equate the relationships for both planets. And this constant is the same for all planets orbiting the same star, as it's dependent on the star's mass and gravitational constant. So what we'd actually write out is b sub x squared over a sub x cubed equals p sub y squared over a sub y cubed equals k. And now let's say we want to solve for py in context of the problem, right? Or p sub y. So by cross multiplying and taking the square root, we can isolate p sub y to find its value in terms of known quantities for planet X, the semi-major axis for planet Y. And this final step provides a practical formula to calculate the orbital period of any planet given the reference orbital period and semi-major axes. So let's just solve really quickly. We have px squared times ay cubed equals py squared a cubed x. And what I should actually have done is kept this on the left side. So I'll just rewrite it quickly. By squared equals p x squared all over right, yeah, and then we do over, sorry guys, I'm getting a little lost in my steps here. Take out py and we get equals root, give me root of this whole expression, p sub x squared times a y cubed x, right? And it's gonna actually, what we can simplify this to, if I'm not wrong, might have actually messed up my steps a bit here, but what you should get, guys, sorry it's a little late where I am, is py equals p sub x ay over ax to the 3 over 2 power, okay? And this can also be rewritten as if you want, as p sub x of root ay over ax cubed. And here is your final proportion. And so if you wanted to solve in, again, you could substitute p sub x for 1 year, a sub x for 1 AU, a sub y for 0.723 AU, or to find p sub y. So let's conclude our little lesson here. Kepler's laws are more than theorems. They're a window into the forces that shape our universe. From the elliptical orbits to the conservation of angular momentum, the harmony of orbital periods, these laws are fundamental to our understanding of celestial mechanics. Thank you for listening, guys, and have a good night.